Hello, this is Elder Tehila from the Covenant of the Open Mind, and you're watching Metaphysics 101. Hail and welcome. Special relativity is a description of the laws of nature based on the observed behavior of light, namely the fact that light always travels at the same speed. And we'll talk about why that's important. First, I want to illustrate an example of how it normally works in regular laws of motion, in Newton's laws of motion, and then we'll throw the corrective factor here from special relativity into the mix to provide a really solid understanding of why this is significant. Imagine a person standing on a train, and imagine that the train is moving at a constant speed. And if that's the case, then this person on the train may not even know that they're moving. You can toss a ball up into the air and catch it, and the ball is not going to fly off into some random direction just because you're moving. All of the physics inside of the train car is the same. The ball is going to move the same way that it would move if you were standing still. You can toss it up and catch it. No big deal. But the reason for that is because you're moving too. If you tossed a ball into the air and then the train suddenly came to a stop, well, then the ball is going to fly across the train car because now you're not moving, so you can't just catch it. So physics inside of a particular frame of reference will be consistent. If you throw a ball across a train and it lands 5 feet away, well, that is exactly what would happen if you were not in a train and if you threw a ball across the room and it landed 5 feet away. Things get interesting when you introduce a second observer. Say there's a person watching you throw a ball as you travel past a train station. They can see you through the window or whatever. Well, you throw the ball and it lands 5 feet away. So you say, oh, the ball has traveled 5 feet. But you're moving and the train is moving. Let's say in the time it takes the ball to hit the ground, the train itself and you and the ball and everything in it traveled 10 feet. To the person who is watching this happen, it will look like it traveled 15 feet. The 10 feet that the train traveled and the 5 feet that the ball traveled itself. So you both agree, within the train car, the ball traveled 5 feet. But you disagree about how far the ball traveled overall because one of you knows that the train is moving and that you have to consider that distance as well. Okay, this is all simple stuff. Of course, if the train is also moving, then the ball travels the distance the train moves plus the distance that the ball moves within the train. Easy. With special relativity, things get complicated. And the reason is because things are moving very fast. So if this train was moving at half the speed of light, okay, for reference, the speed of light is really fast. That's why you'll never observe this kind of thing in your daily life. You have absolutely no frame of reference by which you can personally understand what is going on here. You will never travel this fast. You will never see anything traveling this fast. I mean, the speed of light is fast. I mean, imagine this. You flip on the switch in your room and you can see everything in the room immediately. It's not like everything in the room is suddenly appearing in your mind, okay? Physically, there is stuff going on here. You turn on the light that produces light particles called photons. These light particles travel to the walls and all the stuff in your room and are either reflected or retransmitted back to you. And then your eyes pick up on all these different photons and your brain interprets the photons and then you can see the room. That happens so fast that you would have no idea that's what's actually happening. if someone didn't sit down and tell you. It's not like when you turn the light on, you could look at the light and say, oh, the light is on, but you can't see anything because the light hasn't traveled to the things yet. That doesn't happen. As soon as the light is on, it's already hit all those things and hit your eyes. So light can cross massive distances in practically no time at all. It is so fast. When things are moving that fast, they start to experience weird things. The physics changes because the speed of light is always constant. The speed of light being constant is something that has been measured and observed always. It is always constant. There has been no circumstances under which anyone has ever measured light to travel at a different speed. And this gives rise to so many weird aspects of physics that are not intuitive because they're not things that you see every day. Now let's go back to our train example. Say that a person is on a train that's moving half the speed of light, and say instead of throwing a ball, they are using a laser pointer. So they turn on the laser pointer and the photons, the light particles, travel from their hand across the car and hit the wall on the other side. To the person in the train, the speed of the light particles from their laser pointer is the speed of light. They turn it on and they instantly see it on the wall on the far side of the train. Now, say you're watching this from the train station. How fast is that light moving with respect to you watching it, since the train is moving? Well, it's still moving at the speed of light, right? I just said that. But the distance that it traveled is incredibly different. So you're going to say that the light moved 6 feet. That's how far it is to the far side of the train. I, as the observer, am going to say, no, that light moved 6 feet plus the distance that the train moved, which, because the train is moving really fast, is going to be a lot of distance. For those who know the math, these numbers make no sense. I'm literally just trying to help people understand these concepts without worrying about the numbers too much. So let's say the train moved 100 feet in that span of time. It moved 100 feet and the light moved 6 feet. So I'm going to say the light moved 106 feet. Who's right? Did it move 6 feet or did it move 106 feet? Both. It moved both. It moved both the 6 feet that I'm observing in my point of reference and the 106 feet that it moved in your point of reference. So you might want to say, oh, well, the light in my frame of reference traveled slower. I'm on the train, so the light traveled 6 feet in a second. So that's how fast the light traveled. The speed of light is constant. The speed is the same. I'll do one basic equation here. Speed equals distance over time. So if you're traveling 60 miles per hour, then in 1 hour, you have gone 60 miles. If we are talking about holding the speed constant across these two reference frames, then the difference has to come from the distance and the amount of time that have passed. This affects mass, length, and time. Because all of these different properties of matter, all of these different dimensions, depend on each other. That is what the equation E equals mc squared means. If something is moving really fast, then it will experience an increased amount of mass. It will appear shorter, and time will pass slower for anyone moving at that rate, for anyone inside of that frame of reference. And this is real, verifiable science. This is not made up crap. You get what many describe when this happens as something called length contraction. You have a train. The train literally shortens. Objects that are moving very fast will appear shorter to the person who is observing the object from the outside. In addition to the object appearing shorter, you might experience things like time dilation, where time moves slower for the person who is inside the train than the person who is watching it. So if you're moving close to the speed of light and you turn on your headlights, well, from your vantage point, the headlights are moving at the speed of light, okay? Because in your frame of reference, the fact that you're moving does not change the physics of how light works in your frame of reference. But now you're driving past me. What does your headlight look like to me? It still moves at the speed of light. It doesn't move faster than the speed of light just because you are moving half the speed of light. It's not like your headlight is suddenly moving 1.5 times the speed of light, because light is not like a ball. The ball will appear to have traveled the distance that the ball travels inside the train and the distance that the train travels. That's not true with light. We're both saying, well, this light is traveling the same speed, but from my vantage point, the light is traveling way faster than it is for you, because it's moving a farther distance in the same amount of time. That's not possible. So time has to be passing differently for me than it is for you. Now, you may think, well, this is purely theoretical. It's not. There are corrective factors on satellites because they move fast enough that they get out of sync with the time here on Earth. Very small corrections. So this is where that twin paradox idea comes from, where you can travel at the speed of light for like a year, and when you get back, everyone's going to be older than you are by a substantial amount. One science fiction movie that displays this very well is Interstellar. The physics in that movie are very sound. It does cross into the metaphysics world near the end because we don't know what happens inside of a black hole, and we don't know if what they depict is even possible. Take a different example now. Let's say I'm standing at the bottom of a really tall cliff, and you're standing at the top. So I shoot a light ray from the bottom up to the top. Let's say I shoot a blue light up to you. Well, because of the equation I mentioned before, E equals mc squared, that is actually a more complicated equation, something like E equals mc squared plus c squared times p to the fourth, where p is the momentum. So an object with no mass still has momentum because momentum depends on the speed. So a particle, a light particle, has no mass, but it still has energy. So it's not just like E equals mc squared, but the mass of light is 0, so therefore light has no energy. That doesn't make any sense because everything has energy. So some of the energy comes from the momentum, the velocity. Because of the relationship between mass and momentum and energy, my light, it has no mass. The momentum has to be the same. It's light, so it always travels at the same speed. So what changes? The energy. The frequency of the light changes. As the light escapes the Earth, it loses energy. For a regular object, it would lose momentum, right? If I were to toss a ball up, it would eventually slow down and stop and then return to the Earth. What goes up must come down. With light, that is not true. Light will lose energy, but continue moving because it has no mass. So I will say, okay, well, this light is blue because this is how many times the light oscillates within a certain period of time. Within 1 second, I see 5 oscillations, 5 waves. You say, oh, well, within 1 second, I see 2.5 oscillations. So for you, the frequency is longer. The light has less energy. You might even see the light as being green or yellow because it's red shifting, right? It's moving on the color spectrum towards red as it loses energy. So we might disagree about the color of the light, but what we won't disagree with is how fast the light is moving. It's still moving at the speed of light, period. This same equation is how you know that physical objects can't move faster than the speed of light, because the amount of energy required to move an object at that speed is absolutely insanely large. You'd have to adjust the mass of that object. You would have to give it like an infinite mass, essentially. So what would happen if you could travel at the speed of light? Nothing. You'd be a black hole. You'd be infinitely massive. It doesn't make any sense. The speed of light is the speed limit of the universe. By now, you should understand that if you shoot light from a bottom of a cliff up, that it will lose energy, but not speed. Why can't we travel faster than light? Because if you want to accelerate something to be moving very, very quickly, then that will impact the mass. And you should also know that the passage of time is different for a person at rest and a person that's moving close to the speed of light. If you understand these 3 things, basically, then you understand special relativity. Why is special relativity important to metaphysics, to understanding spiritually what's going on in the universe? What special relativity tells us is that perception matters, but only when you are talking about certain circumstances. If you are talking about certain circumstances, like where a person is moving close to the speed of light, then yes, time passes differently for both of you. But if both people are just sitting on the surface of Earth, then one may perceive time to be passing at a different rate than the other, but it's passing at the same rate for both of them. So the reason special relativity is important in metaphysics is that it is the least well understood theory that is used to justify the most ridiculous of claims. It's important that you understand when the effects of special relativity can be noticed and when they matter. It only matters when people are moving really fast. Special relativity has nothing to do with justifying our perceptions of divinity or the higher planes of existence. It's essentially a way of saying, what are the universal truths here? Because it seems like how you perceive something matters. And physics doesn't like that. Physics doesn't like depending on subjective experience. The goal of physics is to be as objective as possible, to explain what's really happening independent from what any individual person is perceiving. With special relativity, we have the means of doing that. Okay, so for instance, a person on a train could say, the world is passing by outside my window, and the world could say, that person is passing by on the train. Both of those are correct. The person could say, well, I'm not moving, the world is, and be right. And the people outside could say, well, the world's not moving, the train is, and be right. Those are just different ways to think about motion. And it doesn't matter which one you use. Okay? However, say that there are two people on the train who are moving, and they're sitting 5 feet away from each other. Well, if I'm outside the train watching those people move, they are still going to be 5 feet apart from each other. Even if I say, well, the train is moving and I'm not, or they say, well, the world is moving and we're not, it doesn't matter, because there's still going to be 5 feet between each of those people on the train. So the ratio of distance between two objects is the same, is constant. That is a universal truth. But how that distance appears to the different observers in the different frames of reference will vary. So special relativity, when you actually do dig into the math, provides you with a way of saying, this is a subjective truth, and this is an objective truth. So the people out there who are saying everything is subjective and there's no way for you to understand something independent of your perception of it are not 100% correct on that. You will always experience some perception of what's going on that is unique to you and your frame of reference. But there is going to be an objective truth as well, that if you put your own perspective aside and look at the larger system, or rather if you treat your perspective as only one of the many perspectives, then you will find the universal truth. We will find a way, using science, to justify our different ways of connecting with divinity. It just isn't through relativity. If you guys have any questions, please leave a comment or email us, covenantofopenmind@gmail.com. So now you understand special relativity, why it matters, and what it tells us about the physical and spiritual world. I hope this has been helpful. From everyone here at the Covenant of the Open Mind, blessed be.